Okay, this will work. So the last thing we have is Cauchy's integral theorem and multiply connected domains. So I'm just going to repeat that for the record. We did the calculation with z to the n, 1 over z to the n, important as well. And we immediately get a nice application. Actually, everything we're going to do is going to follow from this thing right here. So I took a little time proving it reasonably rigorously. So what we have here, and maybe I'll change the lettering to, we have an oriented curve. Maybe I'll start naming it gamma. We had a little, oh, that's right. We had a little problem with the nomenclature there. I'll bring that up. Okay. So we have an oriented curve gamma, and we have f of z is analytic in and on gamma, by which I mean I was calling it C before, but I was confusing that with the complex set itself. Analytic in and on that curve, and in means within here, or in the curve. And then what we have is integral, this closed integral f of z dz is equal to 0. So that's the first thing. I'll list these things. Now, if you have multiply connected domains, multiple connections. So this was the other thing we had last time. Multiply connected domains. The idea there is you've got your curve here. I'm going to call it gamma 0. And so your function is, say, not defined inside those circles. Not defined inside those circles. But what you can do is turn this into one continuous curve. If you go in here, go clockwise, and back out, and do the same thing all the way around here. In, clockwise, back out, in here, clockwise, and back out. And now you would have gamma 0 is the outside, number of these. So now you still have this here, integral f of z dz. If you did the entire curve here, gamma 0 plus, I'll do it this way, gamma 0 plus gamma 1 plus gamma 2 plus gamma 3. So we're going around this curve. So we started here, in there, clockwise, that's that, okay? So that's one curve that's defined here. But these going to that circle and back out again cancel identically because you're going in the same path and not the same path, okay? So because of that, you could also say that this is equal to, so this is equal to 0. You can also say integral f of z dz around gamma 0 equals the integral f of z dz. Actually, why don't I just do a summation equals summation integral f of z dz gamma sub I equals 1 to 3. But if I brought those to the other side, I would have had to have a minus sign in front of them. Okay? So I have a negative 1 on all of those. But these have clockwise orientation, right? So what I can do is I can absorb the -1 into here and turn it from a counterclockwise orientation into a clockwise orientation. So if we have some symbol for that, so CDZ I equals 1 to 3. I'm just going to write negative gamma so I like that. But the point is now we have a proper counterclockwise orientation on both sides. So counterclockwise, counterclockwise. So that's interesting because suppose we wanted this outside one, but we could just get it by calculating these 3 interior ones. That's going to be the strategy that we follow coming up here. And the third element here that we did last time was we said dz z to the n. I'm just going to write here circle R centered around the origin. Okay. So we've got the complex plane here, and we've got a circle radius R. Okay, that's what we're talking about. That equals 2 pi I for n equals 1 and 0 otherwise for all other n. So that's what we have so far. And this is actually going to take us quite a ways. So it's this first inverse power that is so important in these complex integrals. First inverse power. And by the way, if you look in your notes, it was under Darboux inequality that I wrote some confused stuff in terms of the paths. Question?
So that's a C, the complex variable under C.
Here?
Yeah.
Yeah, that's the complex plane. So we're on the complex plane, and just any circle centered on the origin. Any circle at all. And we're gonna make use of the fact that it's any radius whatsoever that works out. So we did that calculation. So those are the 3 things that we have. And the first thing we're going to do is use these to calculate an interesting integral, and everything that follows is kind of an application of this one here. So anyway, the note here, if you look back at the Darboux inequality, I may have written something. I think I wrote C where I meant just the path C, so I'll start calling it gamma instead of C. Okay. But we'll have plenty of time to use the Darboux inequality again. Okay, so let's see where we are. Cauchy's integral formula, and I want to do an integral first. Let's do an example of this. The next note says the integral formula already. Then we'll do Cauchy's integral formula. So what we want is the integral from minus infinity to plus infinity, 1 over x squared plus 1 dx. This is a known integral. Okay. And if we we were to graph it, if we were to say this is a real integral, then we would have, so x f of x equals 1 over x squared plus 1. Then at x equals 0, it's like this, and it's going to decay out to 0, plus or minus infinity. Okay. So that's what this function looks like. This is the first tangent that will get us to our goal, but that's not the way we want to do it this time. What we're going to do is continue this into the complex plane. So now we're going to consider f of z is equal to 1 over z squared plus 1. And now we're integrating in the complex plane, so I can no longer graph that thing, but what we're going to do is integrate it along here, but not only along here, okay? So I could call this negative r, positive r. That's how we would have defined this when we were learning calculus, and r goes to infinity to define that, the domain, okay? So in the complex plane, now let's look at this. Integral 1 over z squared plus 1 dz equals integral 1 over z plus I times z minus I. I put the dz right there. And now we have the situation, namely at z equals I, we have singularity. So the function's not defined at z equals I. So we're going to do the following path here. We're going to make this r go to plus and minus infinity, but our integration path is going to look like this. This is a semicircle of radius r. Semicircle of radius r. But this is going to give us a little trouble, except here's our path of integration. Go in here, we do a little circle of radius r, and we come back out. And so actually this is a little circle of radius little r, lowercase r, and we have the radius uppercase r. Okay. So Cauchy's integral theorem, what does it tell us about this? If I call this my gamma sub 0 is this outside one, and my gamma sub 1 is this inside one, so gamma sub 0 plus gamma sub 1, it tells us that's equal to 0. This integral is equal to 0 if I go around the outside, but then I come in and do a little circle around that one. Equal to 0. Okay, let's see if we can do this. Or, here, let's do this. Integral negative r dz. I'm going to break this up into z plus I, z minus I, plus integral, I'm just going to make that symbol, that's that upper half there, okay? Upper half of radius is called r, dz plus I, z minus I, plus actually, I'm gonna do equals integral lowercase r. In fact, I can say z minus I equals lowercase r. So this is the inside one, except we're gonna reverse it, do exactly what I had there a minute ago. So dz z plus I, z minus I. So that Cauchy's integral theorem and the multiply connected domain said I could do that. Okay, so this one here is this one. The first one is the one we're looking for when we let r go to infinity. The second one here is this semicircle, and the third one is this little tiny inside circle oriented properly. So we can draw the orientation here to make sure we got it right. Okay. So as r goes to infinity, this one goes to 0 as r goes to infinity. That was the example we did last week with, this week with Darbo's inequality. See example that we calculated. So we showed that this one goes to 0. The reason is, it was just, we did 1 over z squared, and that one went to 0, okay? Because 1 over z squared goes to 0. This one here is the one we want. This is minus infinity plus infinity dx x squared plus 1 when we take r goes to infinity. And what about this one? When r goes to 0, lowercase r, we're going to take to 0. What is this integral going to give us? Okay. When r goes to 0, this one here, gotta have some room for this one. So as lowercase r goes to 0, this one goes to z just is arbitrarily close to I. Okay. So as r goes to 0, we're going to have dz, z plus I goes to 2I, and z minus I is the one we're going to, for r, very, very small. And this is going to be just that arbitrary little circle there. This is going to go to 1 over 2I times 2 pi I. Okay. 2I is going to cancel, and that's just going to be equal to pi. Because this is the one we were looking for, this is going to be equal to pi. So let me make sure I clear up this one here. So for r goes to 0, we have r going to 0, we have 1 over 2I, because that's, z is partially I emphasize 2I. But we still have this dz over z minus I. Okay. So we've got the 1 over 2I, and we're just going to let z equal I plus r e to the I theta. dz, this is a constant, I r e to the I theta d theta, and our integral is going to be 0 to 2 pi I r e to the I theta d theta, and the z minus I is r e to the I theta. They cancel. R. And so we have the 1 over 2I. That was just from the integrand. But the integral we were looking for, that is once again I times 2 pi. 2 pi I. That's that little circle, arbitrary little circle. So we're gonna do enough of these that you just start seeing it and knocking them out, okay? What we did was.
I have to interrupt.
No
We
problem.
got good news.
What?
We got the physics venue, bud.
All right.
We got legitimate
From whom?
from the official people. Because we told them O'Neill stunk, they said, well, what do you really want to have it? And Doug and everybody were there, we got the approval. It's gonna happen here now, Carl.
It's
I just
on
thought I had
film.
to tell
It's
you.
on film.
I just thought I'd tell you. Bud.
Thanks.
You know, one more thing, I told him at the meeting, I said, Carl will be happy. Right on.
Right on. Okay. How'd you like that? The happy department.
Now we just need to get the booth.
Exactly. Now, once we get the booth, we're gonna be happy. Okay. So, you know, when the dust settles, here's what happened. This is very stereotypical. We're always gonna choose or have functions where this contour vanishes when it goes to infinity. Okay. So what we did was this one vanished. The one we wanted originally was this part here. Okay. And so we basically turned that integration into the evaluation of a singularity. So once we've done this a number of times, and there's a theorem that's going to formalize what we did. And in my notes, actually, I do the theorem first, or the integral formula, but this is better. We took it step by step here. And a lot of what we're going to do now is just applications of this Cauchy formula. And you can do some pretty serious integrations. And in particular, when we do our Fourier transform calculations, this is the technique we need in order to do a lot of them, okay? We did one or two, but in general, we're gonna need the entire complex plane to do those things. So anyway, this is a great place to have landed. I'm gonna write down Cauchy's integral formula now, and you'll see that it's just what I did right here. And then it'll get good. Then I'll have a couple of good homework problems. You guys all know Don, right? Fantastic. Okay. Good. Any questions on this so far? Make sense? Yeah. So these techniques, they're amazing. They're amazing, and we're always going to have this feature, right? We want this one to always vanish. And then we can replace a complicated integral just with what's going on at a singularity. Okay, I'm gonna erase all these. So here we go. Cauchy's integral formula, which formalizes what we just did. So Cauchy integral formula. And f of z is again analytic in and on z. In and on, nope, not c, gamma. On gamma. Where's my lesson? Okay. So here we are. We've got gamma. We've got c sub 0. So the formula is this: 1 over 2 pi I integral closed curve f of z dz z minus z sub 0 equals f of z sub 0, excuse me, f of z sub 0, z0 inside gamma is exterior. So this is roughly what I just did in that calculation. Because here we're taking a function and deliberately putting a z minus d sub 0 underneath it, okay? What I had before was a function that was not analytic, that had a first order pole in that form, okay? So the proof of this is really what I just did. So we'll go ahead and call this the proof. See, I can also add z0 here. Z0 is exterior. Then this entire function, f of z that's analytic divided by z minus 0 is also analytic. Okay, it's well behaved. You're outside here. That thing's far away. Right. So the one I'm doing right now, we don't have a z0 inside. It's analytic. Z minus d sub 0 is analytic because this is safely far away. It's analytic. Therefore, Cauchy's theorem gives us that 0. Now, if z sub 0 is interior, this is an interior point, then we just have to go ahead and look at this thing here. With literally the thing we just did, namely, here's our gamma, and we go in here. Okay. F of z over z minus d sub 0. As long as we're on this new curve and avoiding that point, we have Cauchy's theorem for this thing as well. Okay. So yeah, this formula really just does what we did there before. Good. 0. So you're at gamma 0, gamma 1. Remember, right now I have the clockwise orientation. So integral f of z minus z sub 0 on this gamma 0 is equal to f of z dz z minus z sub 0 on this corrected orientation. So the orientation is correct now. So I've replaced the outside integral by the inside integral. Minus gamma 2. And that's on that little tiny one, and now I can do that limit exactly what I did. So, and then as my little r goes to 0, I have f of z sub 0. So I can pull that out there, and then the remainder of that integral dz z minus z sub 0 f of z sub 0 2 pi I, and that gives us the formula. So the example I did before, which is clear as well, is exactly what I did for Cauchy's integral formula. This form, though, plays a big role later on. So the 1 over 2 pi I is less important than the fact that you've got the function divided by z minus z sub 0. Later on, when we do Taylor expansions and stuff, we'll be starting with Cauchy's integral formula. Okay, but now I have a couple of homework type of problems. I will set them up, and we'll just look at them. They're of varying degrees of complexity. just this one. And we'll set it up. Good.
So this problem is gonna be in line.
This one problem, yeah, this will be just a little extension of this. We may actually, I'll write it as a homework, we'll do a little bit of work on it right now. Good, so we've got Cauchy's integral formula. I'll go ahead and leave the left side up here. So let's just call this homework example. And you can make these arbitrarily bad, but here's what we're looking for. We want to get this integral of dx x squared plus 1 x squared plus 2, okay, from minus infinity to plus infinity. And we're going to use the same strategy we did before. Implicitly we're using this, but really we're just going to go directly to back to the integral formula. Okay. So what does this thing look like if you graph it? If you graph it in the xy plane, since it's a real integral, y equals f of x. When x equals 0, apparently it's equal to 2. And it's also decreasing with, it's symmetrical left to right. It's an even function, it's decreasing. So it's really a similar situation to what we had there. Okay. But now there are two poles, so it gets a little more interesting. There are two first order poles. In fact, we're going to go into the complex plane, and we'll just say dz z squared plus 1 z squared plus 2. Actually, did I write 2 in my notes? Let's do 4. It just gives us nicer numbers. Okay, so this is 4. And the technique we're using here is dz z plus I z minus I z plus 2I z minus 2I. So we've got this factorization again. Okay. This complex factorization, and we're living in the complex plane. The integral we want is this one, right? Got the minus r to r. We know that this integral here is going to vanish. This one along the radius r arc. Because not only do we have 2 powers, we even have 4 powers, so we're very safe. Okay, it's going to vanish as capital R goes to infinity. And we now have 2 poles, one at I, which we had before, and one at 2I. So the Cauchy integral theorem with the multiply connected domain means that we can go into here and do a little circle, another one, oops, and come back. So we're going to have to do what we did last time twice. We're going to have to do it twice, but these are, each time we circle this thing, it's safely isolated and it's just a first order pole. Okay. So this integral here, it would be the one we want, r to r, the real one, so dz z squared plus 1, z squared plus 4. And then it would be this one, z minus I equals lowercase r, and the other one would be z minus 2I equals lowercase r. And for each of those, this is where it's interesting, where it's key. For each of these two, so this one's gonna go to 0. This is the one we're looking for. And it's gonna reduce to these two little circle integrals, okay? And each time when you let I go to 0, I'm sorry, when you get lowercase r go to 0 here, in one of them, this is all that's left, and you have to plug in I into these z's here. And in the other one, you've got the z minus 2I, and you have to plug in 2I into those other ones. Right? So we're doing these by hand. When we've done a couple of these, we'll eventually get to the residue theorem where there's a certain recipe, you know, just get the residues. But right now we're doing them by hand, so to speak, so that we can see what's being done at each step. Okay, let's make sure this is the 2I. I'm gonna give everything away, but so what we have here on the right side, this is the one we're looking for. I'll continue this over here. Equals, so this one more explicitly, we've got I'll bracket this out, we've got z plus I, z plus 2I, z minus 2I. So this whole thing is just gonna be evaluated as z equals I. And what will be left is the dz over the z minus I, which is the integral we just did. Okay. That's why in the limit as z minus I equals r goes to 0. In that limit, you just evaluate this stuff. That's essentially the function of this theorem here. And then this one you're just used to, 2 by I. This little circle just usually at 2 by I. And this gives you whatever it gives you. And then you have to do the other one the same way. But now you've factored out the z minus 2I, and whatever's left over there to evaluate at 2I. See what happens. If you can go through the examples we just did and get this one, you'll be in good shape. Then, about a week downstream or a couple lectures downstream, we have what's called the residue theorem, which just does this for any number of them and has a few things to go along with it. But we have a couple of intermediate steps. So for the moment, the reason we know that this one went to 0 is because we have enough powers down here. There's going to be another criterion later that'll help us do other ones as well. But right now, we just know we have plenty of powers. This one vanishes. Okay, good. That's all I've got for you. See what you can do with this one, and the other only had a couple other problems, so that should be good. And I'm tempted to put something like that on the exam, but we'll see. It's not too hard. Okay, good.